energy collectors, DC isolators and DC SPD, our safety switches and surge protectors for the DC side, DC circuit breakers, DCCB, overcurrent protection for DC circuits. Hybrid inverter, the brain. This unit converts solar power, manages battery charging, and can seamlessly switch between grid and battery power. Battery bank, your energy storage, essential for backup power. AC isolator and AC SPD, safety switches and surge protectors for the AC alternating current side. AC circuit breakers, ACCB, overcurrent protection for AC circuits. ATS, automatic transfer switch. This beauty ensures your power stays on during blackouts. Utility grid connection, where we connect to your power company. Load, your home appliances. Let's break down these step 1 calculations for an 8 kilowatt solar power system using 585 watt solar panels. Goal: to determine how many 585 watt solar panels are needed to achieve an 8 kilowatt system. 1. Convert kilowatt to watts. The system size is usually given in kilowatts, kW, but individual panel power is in watts, W. We need to work with the same units. 1 kilowatt equals 1000 watts. Therefore, 8 kilowatts equals 8 into 1000 equals 8000 watts. 2. Calculate the number of panels. Now divide the total desired system wattage by the wattage of a single panel. Number of panels, done, total system wattage, divided by individual panel wattage, number of panels, 8000 watt divided by 585 watts panel. Number of panels approximately 13.67 panels. 3. Round up to the nearest whole number. You can't install a fraction of a solar panel. To ensure you meet or slightly exceed your 8 kilowatt target, you must always round up to the next whole number. Number of panels, Shak, 14 panels. You would need 14 solar panels of 585 watts each to build an 8 kilowatt solar power system. 4. Verify total wattage, optional but recommended. Let's see what the actual total wattage would be with 14 panels. Total wattage equals number of panels into individual panel wattage. Total wattage equals 14 panels into 585 watt panel. Total wattage equals 8190 watts or 8.19 kilowatts. This shows that with 14 panels, your system will actually be 8.19 kilowatts, slightly over your 8 kilowatt target, which is generally a good thing to account for minor losses and ensure peak performance. Step 2. String sizing. Before we dive into string sizing, we need to gather the crucial specifications for both the 585 watt solar panels and the hybrid inverter. These details are paramount for correct and safe string sizing. Let's break down the typical essential specifications you'd need. Understanding solar panel specifications for a 585 watt panel. When looking at a 585 watt solar panel datasheet, you'll primarily be interested in the electrical characteristics at standard test conditions, STC. STC means the panel is tested under ideal laboratory conditions, 1000 watts per square meter irradiance, 25 degrees Celsius cell temperature, 1.5 air mass. Here are the key parameters and why they matter for string sizing. Maximum power, Pmax, 585 watts. This is the nominal power output of the panel under STC. This is the rating we're using to determine the system size. Open circuit voltage, VOC, 49.5 volt. This value can vary significantly between manufacturers for a 585 watt panel, typically ranging from 45 volt to 55 volt or even higher for some advanced designs. This is the maximum voltage the panel can produce when no load is connected, open circuit. It's the highest voltage a single panel can output. Importance for string sizing. VOC is critical for calculating the maximum string voltage, which must never exceed the inverter's maximum input voltage. VOC also increases slightly in colder temperatures, so you need to consider the coldest expected temperature in your location for the most accurate calculation. Maximum power voltage, VMP 41.8 volt. Again, this varies with VOC. This is the voltage at which the panel produces its maximum power. Importance for string sizing. This value is used to calculate the operating voltage of the string. The total string VMP should fall within the inverter's MPPT, maximum power point tracking, voltage range for optimal performance. Short circuit current, ISC, 14.7 amps. This also varies. This is the maximum current the panel can produce when its terminals are shorted. It's the highest current a single panel can output. Importance for string sizing. ISC is critical for calculating the maximum string current, which is essentially the ISC of a single panel when panels are in series, or the sum when in parallel. This value is used to determine fuse and circuit breaker sizing and must not exceed the inverter's maximum input current. Maximum power current, EMP, 14 ampere. This also varies. This is the current at which the panel produces its maximum power. Importance for string sizing, used to calculate the typical operating current of the string. Temperature coefficient. The temperature coefficient is a parameter that quantifies how much the output of a solar panel decreases as the temperature rises above 25 degrees Celsius. A typical temperature coefficient might be minus 0.5% per degree Celsius. This means for every degree above 25 degrees Celsius, the panel's output decreases by 0.5%. Importance for string sizing. The VOC temperature coefficient is essential for calculating the absolute maximum string voltage at the coldest expected temperature, which is a critical safety check against the inverter's max input voltage. Understanding hybrid inverter specifications for an 8 kilowatt system. The inverter datasheet will provide a wealth of information, but for string sizing, we focus on the DC input PV array parameters and potentially the MPPT range. Here are the key parameters and why they matter. Maximum PV input power 10,000 watt or 12,000 watt, often higher than nominal AC output power to allow for oversizing PV array for better performance. This is the maximum DC power the inverter can handle from the solar array. Importance for string sizing. Your total PV array wattage, 8,190 watts from our 14 panels, must be less than or equal to this value. Number of MPPT trackers. 2 MPPT maximum power point tracking. Trackers are electronic circuits that optimize the power output from the solar array. Each tracker can handle independent strings or sets of strings. Importance for string sizing. If you have multiple MPPT trackers, you can design multiple independent strings. This is useful for complex roof layouts or different panel orientations. Maximum PV input voltage, VDC max, 600 volt or 500 volt. Some larger inverters go up to 1000 volt or 1500 volt. But for an 8 kilowatt residential hybrid, 500 to 600 volt is common. This is the absolute highest DC voltage the inverter's input can safely handle. Exceeding this voltage will damage the inverter and void the warranty. Importance for string sizing. Your calculated maximum string voltage at the coldest temperature must always be below this value. This is the most critical safety check for string sizing. MPPT voltage range, VMPPT range or VDC start to VDD max MPPT value, 120 volts to 450 volts. This is the voltage range within which the inverter's MPPT circuit operates efficiently. For optimal power production, the operating voltage VMP of your solar string should fall within this range under most operating conditions. Importance for string sizing. Your string's VMP at expected operating temperatures should ideally stay within this range. The inverter may still operate if the voltage goes outside this range, but it won't be as efficient. The lower end is also important for the inverter to start up. Maximum input current per MPPT, IDC max or IMPPT max. Example, value 15 ampere for a single MPPT or 15 ampere plus 15 ampere for dual MPPT. This is the maximum DC current that each MPPT input can safely handle. Importance for string sizing. The ISC of your string or parallel strings, if applicable, must be less than or equal to this value, with some buffer for safety and temperature effects. 1.25 into ISC is often used for breaker sizing, but the inverter's input rating is a hard limit. Rated AC output power, 8000 watt or 8 kilowatt. This is the maximum continuous AC power the inverter can deliver to your home or the grid. Importance for string sizing. This confirms the inverter matches your desired system size. Battery voltage range if a hybrid inverter with battery input. Example, value 40 volt to 60 volt for a 48 volt nominal battery system. This defines the compatible voltage range for the battery bank. Importance for string sizing. While not directly for PV string sizing, it's crucial for selecting the right battery bank voltage to match the inverter. Next step, once you have these actual values for your chosen 585 watt panel and your specific 8 kilowatt hybrid inverter, we can move on to the actual string sizing calculations with concrete numbers. Great. With the understanding of the key specifications, let's move on to the string sizing for your 8 kilowatt system using 585 watt solar panels and a hypothetical hybrid inverter. I'll use representative example values that are typical for modern high wattage panels and an 8 kilowatt residential hybrid inverter. You must replace these with the actual values from your chosen panel and inverter datasheets for your specific project. Representative example. Specifications. A 585 watt solar panel, hypothetical values at STC 25 degrees Celsius. Pmax, maximum power, 585 watts. VOC, open circuit voltage, 49.5 volts. VMP, maximum power voltage, 41.8 volts. ISE, short circuit current, 14.7 amperes IMP maximum power current, 14.0 ampere temperature coefficient of VOC minus 0.28% per 25 degrees Celsius or minus 0.1386 volts per 25 degrees Celsius using 49.5 volts into negative 0.0028 B8 kilowatt hybrid inverter. Hypothetical values: rated AC output power 8000 watts, 8 kilowatts. Max PV input power 12,000 watts, allows for oversizing the array. Number of MPPT trackers: 2. Max PV input voltage VDC max 500 volts. MPPT voltage range VMPPT range 100 volts to 450 volts. Max input current per MPPT IDC max 20 ampere. String sizing calculations, step by step. We determined earlier that you need 14 panels, 8190 watts total. Now we need to arrange these 14 panels into strings for the inverters to MPPTs. Key principles for string sizing: maximum string voltage, safety check. The string's VOC at the coldest expected temperature must never exceed the inverter's maximum PV input voltage. Operating voltage performance check. The string's VMP at typical operating temperatures should fall within the inverter's MPPT voltage range. Maximum string current, the string's ISC or sum of parallel strings ISC, must not exceed the inverter's maximum input current per MPPT. Step 2a, determine the coldest expected temperature. Solar panel voltage VOC increases in cold weather. This is critical for preventing damage to the inverter. Location: Jeddah, Makkah province, Saudi Arabia. Look up historical lowest temperatures for Jeddah. While generally warm, temperatures can drop. Let's assume a plausible extreme low for calculation. Tmin equals 5 degrees Celsius. This is a conservative estimate for an absolute minimum. Actual might be higher, but better to be safe. STC temperature 25 degrees Celsius. Step 2. Calculate max VOC per panel at coldest temperature. Temperature difference delta T Tmin ESTC equals 5 degrees Celsius minus 25 degrees Celsius equals negative 20 degrees Celsius. Voltage change per panel delta T times VOC temp coef times using percentage minus 20 degrees Celsius times minus 0.28% per degree Celsius equals plus 5.6% increase times new VOC at 5 degrees Celsius equals 49.5 volts. 1 plus 0.056 equals 52.272 volts. Alternatively, using absolute change, negative 20 degrees Celsius times negative 0.1386 volts per degree Celsius equals plus 2.772 volts. So, 49.5 volts plus 2.772 volts equals 52.272 volts. Step 2c, determine the number of panels per string. Iterative process. We have 14 panels and 2 MPPTs. This suggests 2 strings of 7 panels each. Let's test this configuration. Configuration: 2 strings of 7 panels in series per string, 7s. Check 1. Maximum string voltage, VOC, max at Tmin times. Voltage per panel at Tmin equals 52.272 volte. String VOC max, equal number of panels per string, x VOC max per panel. String VOC max, 7 panels, x 52.277 volt per panel, 365.904 volt. Comparison: 365.904 volts, less than 500 volts. Inverters, max PV input voltage, yes. The string length is safe regarding maximum voltage. Check to operating string voltage VMP at STC/typical operating temp. We'll use STC values for a quick check. For more precision, you'd use NOCT, nominal operating cell temperature values, or calculate VMP at a typical operating temperature, 45 degrees Celsius for Jeddah. Voltage per panel at STC 25 degrees Celsius equals 41.8 volts. String VMP equals number of panels per string times VMP per panel. String VMP colon 7 panels times 41.8 volts per panel equals 292.6 volts. Comparison: is 292.6 volts within 100 volts to 450 volts. Inverter's MPPT voltage range, yes. The string length should operate efficiently. Check 3. Maximum string current ISC. When panels are in series, the current of the string is the same as the current of a single panel. String ISC equals 14.7 ampere from panel spec. Comparison: is 14.7A less than 20A inverter's max input current per MPPT? Yes, this is safe for the inverter's current handling. Conclusion for string sizing. Based on these calculations and our hypothetical values, a configuration of 2 strings, each with 7 panels in series, 7S, is suitable for your 8 kilowatt system using these 585 watt panels and this type of hybrid inverter. MPPT1, 7 panels in series. MPPT2, 7 panels in series. Total panels, 7 plus 7 equals 14 panels. Matches our calculated need. Important considerations and next steps. Real-world data. Always use the exact data from your purchased solar panels and inverter. Minor differences in specifications can change these results. Temperature variation. For critical applications, consider the absolute lowest historical temperature for your site. Saudi Arabia generally has high temperatures, but winter lows exist. Roof layout. This calculation assumes you can physically fit 2 strings of 7 panels on your roof without significant shading issues. Real-world roof layout often dictates string lengths. Shading. If a string experiences partial shading, it can drastically reduce its output. For roofs with complex shading patterns, you might consider micro-inverters or optimizers instead of string inverters, or design shorter strings to minimize shading impact. Voltage drop. For long cable runs, calculate voltage drop to ensure it's within acceptable limits, typically less than 1 to 2%. Parallel strings. If an inverter only has 1 MPPT but can handle more current, you might string panels in parallel. For example, 2 strings of 7 panels, 7S, 2P, meaning 2 7-panel series strings connected in parallel to that single MPPT. However, our example inverter has 2 MPPTs, making 7S per MPPT the most straightforward design. This detailed string sizing helps ensure your system operates safely, efficiently, and maximizes power production from your solar array. Alright, let's move on to the crucial DC side protection components for your 2 strings of 7 panels each, 7S configuration for MPPT1 and 7S for MPPT2. This involves selecting the appropriate DC disconnect switch, DC isolator, DC surge protective device, DC SPD, and DC miniature circuit breaker, DCMCB. Again, I will use the hypothetical values established in the previous step. You must use the actual specifications from your solar panels and inverter, as well as the chosen DC components for your project. Let's assume a setup where each string has its own MCB and SPD, and then a main DC isolator before the inverter, or individual isolators per string if preferred. For simplicity and good practice, we'll size components for each of the 2 independent strings. Component 1, DC circuit breaker, DCMCB, for each string. The DCMCB protects each string from overcurrents and short circuits. Rating criteria. Voltage rating must be greater than or equal to the maximum open circuit voltage of the string at the coldest temperature. Current rating must be able to carry the string's normal operating current but trip on fault conditions. The standard is typically 1.25 into ISC for continuous current applications. As per NEC guidelines, though IEC standards might have slight variations, this is a common practice. Calculations for 1 string, 7 panels. Required voltage rating. Greater than or equal to string VOC max equals 365.904 volts. Standard availability. DCMCBs typically come in standard voltage ratings like 400 volts, 500 volts, 600 volts, 1000 volts. Selection. A 400 volt or 500 volt DCMCB would be appropriate. Choose the next standard rating above your calculated max voltage. Required current rating 1.25 times. String ESC 1.25 times 14.7A equals 18.375. Ampere standard availability. DCMCBs typically come in standard current ratings like 10A, 16A, 20A, 25A, 32A. Selection. A 20A DCMCB would be the correct choice. Next standard rating above 18.375 amps. DCMCB specification for each string. 2 pieces 400 to 500 VDC 20 ADC, MCB1 for each string component, 2 DC surge protective device, DC SPD. For each string, the DC SPD protects the inverter from voltage surges, lightning strikes coming from the solar array. Rating criteria. Maximum continuous operating voltage, UC, must be greater than or equal to the maximum open circuit voltage of the string at the coldest temperature. Nominal discharge current, IN, the current level at which the SPD can repeatedly discharge surges, typically 20 kA for type 2. Maximum discharge current, Imax, the maximum current the SPD can safely discharge once, typically 40 kA for type 2. Calculations for 1 string 7 panels. Required UC rating. Greater than or equal to string VOC max equals 365.904 volts. Standard availability. DC SPDs typically come in standard voltage ratings like 500 volts, 600 volts, 800 volts, 1000 volts. Selection. A 500 volt or 600 volt DC SPD would be appropriate. Choose the next standard rating above your calculated max voltage. Current handling type 2 SPDs with IN 20 kA and Imax equals 40 kA are common for residential PV systems. DC SPD specification for each string. 2 pieces, 500 to 600 volts, DC, type 2 20 kA per 40 kA, DC SPD, 1 for each string. Component 3, main DC isolator switch. This provides a manual means to completely disconnect the entire PV array from the inverter for maintenance or emergency. Rating criteria. Voltage rating must be greater than or equal to the maximum open circuit voltage of the combined parallel strings if they were connected in parallel at the isolator point before the inverter, or the highest voltage of any string if connected individually. In your case, since the strings go to separate MPPTs, it could be separate isolators or one isolator per MPPT. If a single isolator handles both, its voltage rating must still exceed the max voltage of one string. Current rating must be rated for the sum of the short circuit currents of all strings connected to it, multiplied by a safety factor, typically 1.25. Calculations. Assuming one main DC isolator handling the combined currents if inverter had one MPPT, or for a dual input isolator. Required voltage rating greater than or equal to string VOC max equals 365.904 volts. Standard availability. DC isolators typically come in 400 volts, 500 volts, 600 volts, 1000 volts. Selection. A 500 volts or 600 volts DC isolator. Required current rating. Diagram shows two DC isolator before the inverter. Let's calculate current for DC isolator. Total ISC equals 14.7 amperes per string. Required current rating equals 1.25 times 14.7 amps equals 18.375 amps. Standard availability. DC isolators come in ratings like 20 amps, 32 amps, 40A, 63A. Selection. A 20A or 32A DC isolator. A 20 amp might be borderline depending on precise standards. 32 amp provides more buffer. Main DC isolator specification. 2X. 2Ps 500 to 600 volts. DC 20 to 32 amps DC isolator depending on how it integrates with the two MPPT inputs. Important note on DC-DB design. For two strings churn 2 MPPTs, a common arrangement is PV string 1 DCMCB 1 DCSPD 1 inverter MPPT 1 input, PV string 2 DCMCB 2 DCSPD 2 inverter MPPT 2 input, and then 2 DC isolator is often placed at the inverter's side or as part of the overall DC-DB that receives both string inputs. Some inverters have integrated DC isolators, eliminating the need for an external one. Always check your inverter's features. Therefore, for your DC-DB components, you'd typically need 2x DCMCB, 400 to 500 volts DC, 20 amps, 2x DCSPD, 500 to 600 volts DC, type 2 20 kiloohms, 40 kiloamps, 2x main, DC isolator, 500 to 600 volts DC, 20 to 32 amps. This ensures robust protection for your solar array and inverter on the DC side. Next, we would typically look at the battery protection DCCB number 2. DCCB number 2, the battery circuit breaker, is absolutely critical for protecting the battery bank and the inverter's battery input/output. To size this correctly, we need to know two main things. The nominal voltage of your battery bank. For an 8 kilowatt hybrid system, a 48 volt battery bank is the most common and efficient choice for residential systems, while 24 volts is sometimes used for smaller systems. 48 volts significantly reduces the current, allowing for smaller, more manageable cables and breakers. So, we'll assume a 48 volt battery bank for these calculations. The maximum continuous charge-discharge current that the inverter can push to pull from the battery bank. This is the critical parameter usually found in the inverter's specifications under battery or charge-discharge current. Representative example specifications, recap and new assumptions. A 8 kilowatt hybrid inverter, hypothetical values. Rated AC output power, 8000 watts, 8 kilowatts. Nominal battery voltage, 48 volts. DC, assumed common for 8 kilowatt systems. Max charging current from PVAC to battery, 120 amps, a common value for an 8 kilowatt. Inverter with substantial charging capability. Max discharging current from battery to inverter not load, 190 amps. This can be calculated from the inverter's AC output, 8000 watts divided by 48 volts, approximately 166.67 amps. Inverters often have a higher maximum discharge current listed to handle surges. Let's use a slightly higher value like 190A as seen in some datasheets. B. Battery bank hypothetical values. Nominal voltage, 48 VDC. We don't need the AH capacity for the breaker sizing directly, but it's important for overall system design. DC circuit breaker, DCCB number 2, calculation for battery protection. The DCCB number 2 protects the battery bank and the inverter's battery terminals from overcurrents due to faults, short circuits, severe overloads. Rating criteria. Voltage rating must be greater than or equal to the maximum battery bank voltage, float voltage for lead acid, or fully charged voltage for lithium ion, which can be slightly higher than nominal. For a 48 volt nominal system, this usually means a breaker rated for at least 60 volts DC or 80 volts DC. Current rating must be able to carry the maximum continuous current that the inverter can draw from or push to the battery. This is typically determined by the larger of the inverter's max charge or max discharge current multiplied by a safety factor. The standard safety factor for continuous loads in DC circuits is usually 125% as per electrical codes like the NEC. Calculations: determine max current. Compare the inverter's max charging current and max discharging current. Max charging current 120 amps. Max discharging current 190 amps. The maximum continuous current expected through the breaker is 190 amps. Required current rating for breaker. Breaker current max continuous current x safety factor. Breaker current 190 amps times 1.25 equals 237.5 amps. Required voltage rating for breaker. For a 48-volt nominal battery system, the fully charged voltage can go up to around 58 volts for lithium iron phosphate or 60 volts for lead acid. Selection: a 60 VDC or 80 VDC. DC circuit breaker would be appropriate with 80 VDC providing more headroom. Some go up to 100 volts DC or 150 volts DC, which is also perfectly fine. Final DCCB number 2 specification: 1x 1 piece, 60 to 80 volts DC or higher, 250 amp DC circuit breaker. Important notes: inverter manual is king. Always refer to your specific hybrid inverter's manual. It will often explicitly state the recommended DC breaker size for the battery connection or provide the maximum battery charge discharge currents. Some high-end inverters might even have their own integrated battery disconnects or fuses. Battery BMS. If you're using lithium-ion batteries, e.g. LiFePO4, they will have a battery management system, BMS, that also limits charge-discharge currents and provides its own protection. However, the external DCCB number 2 is still crucial as a main disconnect and for overall system safety, protecting the cables and inverter from external faults. Cable sizing. This breaker current also dictates the minimum size of the DC battery cables. Cables connecting the battery bank to the inverter and therefore running through this breaker must be rated to handle at least 237.5 amps continuously with minimal voltage drop. This will typically require very thick cables, e.g. 20 AWG or 70 mm squared or larger, depending on length and temperature. This calculation ensures that your battery bank and the inverter's connection to it are adequately protected against excessive current, which could lead to overheating, cable damage, or even fire. Okay, let's calculate the components for the AC distribution board, ACDB, for your 8 kW hybrid solar power system. This includes the AC-SPD AC-MCB for the inverter output, the main AC isolator, and the MCB for the loads. To perform these calculations, we'll use the inverter's AC output power and the standard AC voltage for a residential system in Jeddah, Saudi Arabia, which is typically 230 volts AC, single phase. Representative example: specifications, recap and new assumptions. A 8 kW hybrid inverter, hypothetical values. Rated AC output power P, 8000 watts, 8 kilowatts. AC output voltage 230 volts. AC frequency 50 Hz. Step 4. ACDB components calculation. 1. Calculate maximum AC output current from inverter. This is the maximum current the inverter can supply to your home's loads or to the grid. Formula: IAC max equals P/V for single phase, assuming power factor is close to 1. Calculation: IAC max equals 8000 watts / 230 volts, approximately 34.78 amps. 2. AC miniature circuit breaker, AC-MCB for inverter output. This MCB protects the wiring from the inverter's AC output terminals to the ATS load and the inverter itself from overcurrents. Rating criteria: voltage rating must match the system voltage, 230 volts. Current rating must be greater than or equal to 1.25 times the maximum continuous AC output current of the inverter. This 125% rule is a standard safety factor for continuous loads. Calculations: required voltage rating 230 volts. Selection: a 230 volt or 240 volt single phase AC MCB. Required current rating: 1.25 times IAC max, 1.25 times 34.78 amps equals 43.475 amps. Standard availability: AC MCBs typically come in ratings like 20 amps, 25 amps, 32 amps, 40A, 50A, 63A. Selection: a 50 ampere AC MCB would be the correct choice. Next standard rating above 43.475A. AC MCB specification: inverter output 1 piece 230 volts / 240 volts AC, 50 ampere MCB, C curve for general use. 3. AC surge protective device, AC-SPD. This SPD protects the AC side of the system inverter loads from voltage surges coming from the utility grid or internal switching events. It's typically installed at the main distribution board or close to the grid connection point. Rating criteria. Maximum continuous operating voltage (UC) must be suitable for the system's nominal voltage. For a 230-volt system, a SPD rated for 275 volts AC or 320 volts AC is common. Nominal discharge current (IN), the current level at which the SPD can repeatedly discharge surges without damage, 20 kiloamperes. Maximum discharge current (Imax), the maximum current the SPD can safely discharge once, 40 kiloamperes. Type typically Type 2 for residential installations. Calculations. Required UC rating 230 volts. Selection. A 275 volt AC or 320 volt AC SPD. Current handling. Standard Type 2 ratings are usually sufficient. AC SPD specification 1 piece, 275 volts/320 volts. AC Type 2 20 kiloamperes/40 kiloamperes. SPD 1P plus N or 2P depending on configuration charge wiring. For single-phase 230 volts, a 2-pole LN or 1P plus N configuration is common. Fourth, main AC isolator. This provides a manual disconnect point for the entire AC system, isolating it from the utility grid. It's a critical safety device, often located near the main utility meter or service entrance. Rating criteria. Voltage rating must match the system voltage, 230 volts. Current rating must be rated to safely carry the maximum expected current from the utility, your main service breaker rating, or the maximum inverter output, whichever is higher with some safety margin. It typically needs to be rated for at least the total system load plus potential backfeed from the inverter. Calculations. Required voltage rating 230 volts. Selection. A 230 volt or 240 volt AC isolator. Required current rating. This isolator handles the flow of power both to and from the grid. It should be rated for the sum of the inverter's maximum output current and any other significant parallel load on that circuit, or simply sized to match your home's main service breaker if it's the main disconnect for the entire house. For safety, it must be able to interrupt the full fault current. A common approach is to size it for at least the main breaker of your home or slightly above the inverter's maximum output if it's solely for the solar connection. Given the inverter output of 34.78 amps, approx 35 amps, and typically a home's main breaker being 63 amps or 100 amps. Selection. A 63 amp or 80 AC isolator would be a safe choice, ensuring it can handle both the inverter output and common household loads. Some regulations might require it to be equal to or greater than your main incoming utility breaker. Main AC isolator specification 1 piece 230 volts/240 volts AC, 63 amps or 80 amps AC isolator, 2-pole for single phase, 5 MCB for load after ATS. The diagram shows the ATS output connecting to the load. This MCB, or the main breaker of the critical load panel, protects the final load circuit wiring and the connected appliances. Its sizing depends on the maximum power the inverter can supply to the loads. Rating criteria. Voltage rating must match the system voltage, 230 volts. Current rating should be based on the maximum current that the inverter can supply to the loads. This is essentially the same as the ACMCB for the inverter output calculated earlier. Calculations. Required voltage rating 230 volts. Selection. A 230 volt or 240 volt AC MCB. Required current rating 1.25 times. IAC max 1.25 times. 34.78 amps equals 43.475 amps. Selection. A 50 ampere AC MCB. AC MCB specification for load 1 piece 230 volts/240 volts AC 50 ampere MCB C curve. This would be the main breaker feeding your critical load panel or circuits directly fed from the ATS. Individual circuits within that load panel would have their own smaller MCBs. The next step, proper earthing connections. You've done the hard part. The solar panels are on the roof, the inverter is mounted, and the batteries are in place. But before you power everything on, there's a crucial next step that's all about safety and system longevity, grounding or earthing. We're going to break down the essential earthing points for a complete 8 kilowatt solar power system. We'll walk you through each connection to ensure your setup is safe, reliable, and up to code. 1. Grounding the PV array. The journey starts right up on the roof with your solar panels. Even though the wiring inside is DC, the metal frames of the panels and the metal racking they're mounted on must be grounded. You'll need a green insulated copper grounding wire specifically for this purpose. Use a dedicated lug or a grounding clip to connect the frame of each solar panel to the metal racking. Then, run a continuous wire from the racking down to your main grounding system. This protects the entire array and prevents a buildup of static electricity. 2. The DC combiner box and inverter. Next, follow that DC wiring down to your combiner box. The metal enclosure of this box needs to be grounded, just like the panels connected to your main grounding wire. Now for the heart of the system, your inverter. Your inverter has a dedicated grounding terminal, usually marked with the universal ground symbol. This is where the DC side grounding and the AC side grounding often converge. Make sure to connect a solid ground wire to this terminal according to the manufacturer's instructions. This is one of the most critical connections you will make. 3. The battery bank. For your battery bank, if it's in a metal rack or enclosure, that metal needs to be grounded. This provides an additional layer of protection against any potential faults. Connect the metal rack to the main grounding wire. Some advanced battery systems may also have a specific grounding terminal, so always check the manufacturer's manual. 4. The AC side components. Now we move to the AC side of the system, which is equally important. The metal enclosures of your AC disconnect, the transfer switch, if you have one for grid backup, and your main breaker panel must all be grounded. In a standard electrical panel, the ground wire is connected to the ground bus bar, which is bonded to the panel's metal chassis. This is a standard and crucial part of the safety circuit. Ensure all your AC components have this bond and are tied back to the main ground. 5. Tying it all to earth. Finally, all these grounding wires, from the solar panels, the inverter, and the AC panels, must be tied together and connected to your main electrical services, earth electrode or ground rod. This is the final and most important connection, providing that safe path directly to the earth itself. Make sure this connection is solid, corrosion resistant, and low resistance. This is the heart of your grounding system. It's what makes all the other connections effective. So, to recap, proper grounding for your 8 kilowatt solar system involves a continuous path from the solar panel frames and racking through the inverter chassis, the AC components, and finally, to your main earth electrode. This isn't a step to be skipped. It's the difference between a safe, reliable system and a potential hazard. A quick but important disclaimer. Always consult with a qualified electrician and follow your local electrical codes. High voltage DC and AC systems are dangerous. If you're not comfortable with this process, hire a professional. If you found this helpful, hit that like button, subscribe for more solar tips, and let us know in the comments if you have any questions. Thanks for watching, and we'll see you in the next one.